So, good morning everyone. Today I am going to explain about the linear wave shaping and high pass RC circuit for some input signals. So, first of all, we are going to discuss about the basic definition of linear wave shaping circuit. It is the wave shaping is the process of changing the shape of the input waveform by processing it through a small circuit that consists of resistor and capacitor. So whenever we can process the input signal to the circuit through the circuit, the shape of the input waveform is changed and produced at the output terminals. That type of wave shaping circuit is called as a linear wave shaping circuit. So linear wave shaping circuits are basically classified into two categories. One is low pass RC circuit, next one is high pass RC circuit. So first of all, we discuss about the high pass RC circuit. So this is the basic circuit diagram of high pass RC circuit. So it is consisting with a resistor and a capacitor. Here input signal is applied to the capacitor and output is taken across the resistor. Input is applied to the capacitor and output is taken across the resistor. Here Vi represents the input signal, V0 represents the output signal, I represents the current flowing through the circuit. I represents the current flowing through the circuit. Now, the basic operation of the circuit is divided into three cases. First one is when the input signal frequency is 0. Second case is when the input signal frequency is infinite. Third case is when the input signal frequency is some finite value. Now, coming to the first case, when the input signal frequency is 0, we already know the reactance of the capacitor, that is Xc is equal to 1 by 2 pi Fc. That means when the input signal frequency is 0, the capacitor offers infinite reactance. When the input signal frequency is 0, the capacitor offers infinite reactance. For the infinite reactance, the capacitor acts as a open circuit. For the infinite reactance, the capacitor acts as a open circuit. So when the capacitor acts as a open circuit, there is no movement of flow of carriers from this point to that point. When the capacitor acts as a short circuit, there is no flow of carriers from this point to the circuit. So whenever it acts as a open circuit, 1 minute. Whenever it acts as an open circuit, there is no flow of carriers from input to the output terminals. Therefore, correspondingly, the output voltage V0 is equal to 0. Now, coming to the second case, when the input signal frequency is infinite, according to the reactance of the capacitor Xc, that is equal to 1 by 2 pi Fc, the reactance of the capacitor is 0. When the capacitor reactance is 0, it acts as a short circuit. Therefore, whatever the input voltage or waveform appears at the input terminals is transferred to the output terminals. Now, at the 0 frequency, the capacitor acts as a open circuit. Therefore, output is equal to 0. At infinite frequency, the capacitor acts as a short circuit and output is equal to input. Now, when the input signal has some finite value instead of 0 or infinite, the reactance of the capacitor starts decreasing from infinite. When the input signal has some finite value instead of infinite or 0, the capacitor reactance starts decreasing from infinite value. Whenever the capacitor reactance starts decreasing from infinite value, it slowly starts the flow of current through it. So because of this current, some voltage is developed across the resistance R. That voltage is appeared as the output terminal. So whenever the input voltage goes on increasing in some finite value, the reactance of the capacitor starts decreasing and it allows more current through it and more voltage developed across it, and the output voltage also goes on increasing. That means at some finite value, by increasing the amplitude of the input, by increasing the frequency of the input signal greater than 0, the reactance of the capacitor decreases and it allows more current and more voltage is developed across the resistor, and finally output voltage also goes on increasing. That means from this it is clearly indicated here. It is clearly indicated here. So check that at 0 frequency the output is 0. At infinite frequency the output has maximum value. At some finite frequency, the reactance of the capacitor starts decreasing and the output voltage starts increasing. So the output voltage starts increasing up to the certain value. That certain value is called as lower cutoff frequency. Whenever the input signal frequency crosses this frequency, the output voltage remains almost constant. That means there is a variation of the output response between these two frequencies, that is from 0 frequency to the cutoff frequency. Less than or equal to 0, the output response is 0. Greater than the lower cutoff frequency, output has the maximum value. Only there is a change in the output response between these two frequencies, that is from 0 to lower cutoff frequency. So from this circuit is clearly observed that the circuit allows all the frequency components without all the high frequency components without any attenuation and attenuate all the low frequency components. Hence it is named as high pass RC circuit, and this represents the frequency response of high pass RC circuit. On x-axis it is frequency, on y-axis it is gain. Here 1 represents the maximum value, maximum output response, and 0.707 represents the amplitude of the output response at lower 3 dB frequency. FL represents the lower 3 dB frequency. Now apply KVL to the figure here. That means for a high pass RC circuit, apply KVL to this one. Therefore, the input Vi is equal to voltage across the capacitor plus voltage across the resistor. That means Vi is equal to Vc plus Vr. So that is mentioned here. Vi is equal to Vc plus Vr. So here in equation 1, Vc represents the voltage across the capacitor. It can be written as Vc, that is equal to 1 by C into integral of I into dt. And Vr is equal to V naught. Now substitute Vc value, Vr value into this equation. Therefore we get Vc, that is 1 by C into integral of I into dt, plus Vr, that is equal to V naught, and that is equal to Vi. Now in equation number 2, I represents the current flowing through the resistor. That I is equal to volt, that I is equal, I represents the current flowing through the resistor. That I is equal to VR by R or V naught by R. V naught by R. So that is clearly represented here. VR by R, that is equal to V naught by R. Now substitute the value of I into equation number 2. Therefore, 1 by C into integral of, that is I, V naught by R into dt plus V naught, that is equal to Vi. Now differentiate the equation with respect to t. Therefore, whenever you can differentiate, first term is V naught by RC plus dV naught by dt, that is equal to dVi by dt. Now it can also be written as V naught by RC plus dV naught by dt plus dVi by dt, that is represented with equation number 4, and this represents the general expression for high pass RC circuit. This represents the general expression for high pass RC circuit. Now high pass RC circuit as a differentiator. Now to do this, let us consider the expression for high pass RC circuit, that is V naught by RC plus dV naught by dt is equal to dVi by dt. Therefore, in this Move V naught by RC to the right side. Therefore, dV naught by dt that is equal to dvi by dt minus V naught by RC. Now, if the time constant is equal to C, RC, that is as equal to far less than r tau, if the time constant is far less than the time period of the input signal, then the transient response is insignificant and steady state response is predominant. So what is the time, what is this? This is the transient response, this is the steady state response. So if RC is far less than t, the transient response is ignored and steady state response is considered. Therefore, V naught by RC is equal to dV naught by dt. Therefore, V naught is equal to RC into dVi by dt. Therefore, here RC is the constant value. Therefore, V naught is directly proportional to the d by dt of Vi. That means the output is the derivative of the input signal if the value of the time constant is far less than the time period of the input signal, and it behaves as a differentiator. So that is about the basic of the circuit. Now coming to the response of high pass RC circuit for sinusoidal input signal. So whenever we can apply a sinusoidal input signal, what is the response produced by the circuit? That is going to discuss now. Now here, whenever you can apply a sinusoidal waveform, the voltage across the capacitor also varies sinusoidally. The voltage across the capacitor also sinusoidally, and the current flowing through the resistor are also in sinusoidal motion. Therefore, the output voltage developed across this resistor is a sinusoidal waveform. That means if you apply a sinusoidal waveform, the shape of the output response produced by the high pass RC circuit is also in sinusoidal nature. That means for the sinusoidal signal, the high pass RC circuit cannot behave as a wave shaping circuit. Wave shaping circuit. Here Vi of S represents the Laplace transform of the input signal, and 1 by Cs Laplace transform of capacitance, capacitor current, and V naught of S. This represents the frequency versus gain response of high pass RC circuit we already discussed. Now let us define the gain of the circuit. Gain is nothing but output by input. Here output is V naught of S, input is Vi of S. Therefore V naught of S by Vi of S, that is equal to V naught of S is equal to R by total, that is Vi of S means that is this by Vc plus Vr, that is Vi of S, that is R plus 1 by Cs. Therefore, in the denominator take R as common, R cancel, therefore 1 by 1 plus 1 by S RC. Now, when S is equal to j omega in this equation, therefore A is equal to 1 by 1 minus j by omega RC. Because j is moved to numerator, that's why we get minus j. Therefore, that is equal to 1 by 1 minus j by 2 pi f RC. Here omega is equal to 2 pi f. Now apply modulus to this equation. Therefore, mod A, that is equal to 1 by square root of 1 plus 1 by 2 pi f RC whole square, and an angle of theta is equal to minus tan inverse of 1 by 2 pi f RC. This represents the frequency versus gain response mathematical expression. Frequency versus gain response mathematical expression at lower cutoff frequency, that means at A is equal to 1 by root 2. At a lower cutoff frequency, mod A is equal to 1 by root 2. Therefore, and that means F is equal to F1. Then mod A is equal to 1 by root 2, that is equal to 1 by square root of 1 plus F by F1 whole square. Therefore, it can also be written as that is equal to 1 plus 1 by 2 pi F1 RC whole square, that is equal to 2. Take numerator as cancel. Therefore, 2 minus 1, move this 1 to right side, 2 minus 1, 1. 1 by 2 by F1 RC, that is equal to 1. Therefore, F1 is equal to 1 by 2 pi of RC. So this is the expression for the lower 3 dB frequency of high pass RC circuit. So we already shown this in graph F1. So this F1 is equal to 1 by 2 pi of RC. F1 is equal to 1 by 2 pi RC. Now we also know that mod A is equal to 1 by 1 minus J into F1 by F. Here F1 is equal to, what is F1? F1 is equal to 1 by 2 pi RC. And F is directly represented here. F is directly represented here. So therefore 1 by square root of 1 plus F1 by F whole square. When the input signal frequency is infinite, mod A is equal to 1. Because when F is infinite, this value becomes 0. When it is 0, square root of 1 is 1. 1 by 1, 0. Mod A, 1. When F is equal to F1, 1 by root 2. That means 0.00707. That is clearly depicted here. When F is equal to F1, its magnitude is 0.707. When F is equal to infinite, its magnitude is 1. That is clearly represented here. So this is the response of high pass RC circuit for sinusoidal input signal. Thank you so much for your patient listening.